Yeah, so this is the first episode of Progress.FM. I'm Tyler. The point of this podcast really is just to share like cutting edge technology in the privacy and ZK space, and we'll probably expand other stuff at some point. But yeah, do you want a quick intro?
Yeah, no, I'm Andy. I work more on the product side on the PSE team. I'm excited.
Cool.
I'm Carlos, and I'm also working on PSE in the ZKVM team.
I'm Yigit. I'm currently a drop-in for Surex Park.
Cool. So you are working on a pretty interesting project that is a combination of ZK and MPC. Could you tell us like just a quick overview of what it is and how it works?
Yes, so this game is supposed to be one of the simplest examples of a game that uses both ZK and MPC. And as a very brief intro, it's like a chessboard, and you have two chess kings that move like two chess kings. And the catch, what makes the game interesting, is that number one, you don't have a trusted third party, and number two, the only squares that a player can see are the squares that are immediately around them. So if you think about it in chess terms, it's only the squares that the kings can move to. So like to the 8 squares around them. And so because you have no trusted third party and you can only see those squares and you're on the same board, what essentially happens is that there are two private states that need to be updated at the same time. So these private game states are interacting with each other in a sense. So I think that's the main thing that makes this game different than other ZK games, and that's pretty much intentionally so, because that's how I made the game in the first place. I can also explain the background a bit of the game, like why I decided to make this game.
Yeah. You were telling me that a similar thing exists on chess.com, right? Like a
Yes.
Yeah.
So it's actually there's this variant called dark chess.
Mm-hmm.
It's a variant of actual chess, and it was being played in the past, and also in the physical world. And the idea was you could only see the squares where your pieces are, and the squares where your pieces can move to. And so in the physical world, what they were doing was there were two curtains and three boards, one board in between two curtains, and one board beyond one curtain, and the other board on the other side. So the middle board was the board of the referee, and the two players were sitting on the edges, basically. And so when you make a move as a player, the referee was checking your board, coming to the center board, making that move over there, and obviously the referee's board has all the pieces, so they can see everything. And they make the move, and then they calculate, okay, they just moved their queen, and now they can see this pawn, they can now see this bishop, and then they were going to the other person, they were updating their boards according to that, and then I guess you also need to go back to the actual mover and update that board too. So after a single move, they were doing all the stuff, just directly calculating and then physically changing the two boards. And obviously now we have more practical things, and chess.com has essentially this variant available. They have a variants page, and it's listed as fog of war over there, not dark chess, but it's essentially the same idea. There might be some small changes from the historical dark chess, but it's the same idea. But unsurprisingly, and obviously, there's a trusted third party in that dark chess, and that's why chess.com did not really need more encryption than, I guess, HTTPS for securing connection. Other than that, no crypto. But yeah, so this game, as you might have realized, is just the simplification of dark chess.
Mhm.
You know, I was initially thinking of implementing dark chess, and then I realized I'm more interested in solving this cryptographic challenge rather than actually implementing, I don't know, castling, program parameters is not really that I'm interested in. I know it's just, and also you can obviously, once you solve the problem for a small game, you can always extend, right? You can always add more pieces. You can always add different views. Like, in the game that I'm describing, you can only see the squares around you. But you can, to make it more realistic, you can make a cone. Right? You can only see a cone.
Mhm.
In that case, you can get more interesting things, like you can see the opponent, but the opponent can't see you. Because let's say you're looking at them, you're seeing them over here, but they're looking here. Whereas in the game I have, it's only two kings, and if you can see them, they can also see you.
Yeah.
So you can always add these things later. So the game that I'm working on is the simplest version of such games in this family that has the cryptographic challenge, but it is the simplest thing that I can think of. Basically. So the goal is to first fix the cryptographic challenge. And some history about me trying to find this game. This is summer 2022. I was learning about ZK battleship stuff.
Battle zips.
Yes, stuff like that. But it turns out there are just many and many such ZK battleship implementations. They all have basic same idea, right? I know there are some small changes in the rules of battleship, but for those, I guess, listening and for those 20 years in the future, how we play battleship in 2023 is there are two ship configurations. You have your own ship configuration, and you place them in such a way, and then the opponent does the same thing, and you sort of make a hash commitment to your ship configuration, and then the shots are public, right? So let's say I send a missile or whatever, or an arrow to x equals to y equals 2, and then it's public, and then they reply to me saying, here's a zero knowledge proof that proves that you missed, and what you do, the structure of the circuit is something like they input their private ship configuration, they input your public attack coordinates, and then the output is 1 or 0. And then now it's their turn or stuff like that, just going back and forth.
So we could say that for the people that is listening, basically, we have agreed upon a way on which we have represented our initial ship configuration, right? And there's no way on which any of the players can cheat during all of the rounds that we are doing. So guaranteeing that if you shot a missile and they gave you a proof that this missile went to the water, to put it in some sense, so you get no hits on your opponent, there's no way in which then the opponent can reconfigure the ships, to put it in some sense, so that adjusts to where you are shooting or stuff like this, right?
Yeah, there's basically no dodging that you can do.
Okay.
And
And this is because of the hash. The hashing is public of all the
Yes.
fields. Or
Yes.
okay,
yes,
and you have to submit a proof every time you
yes.
receive. Okay.
And I think it will be worth mentioning, there are actually ways that you can play this, I think, without using zero knowledge proofs and without interesting crypto stuff. Like what you can do is you can just summon the hash, and then during the process, you can just say you missed or you hit, without any zero knowledge proofs. And then at the end, when it's like a judgment day, right? You say you won in quotes, but then you show them, but it turns out you were actually lying some stuff. But in that version of the game, the opponent does not learn that you're cheating during the game.
Until
They
the
can-
end.
yeah, exactly.
Yeah.
So there are variants that don't use ZKP for P2P, but there are drawbacks. There are some. It's a preference, and if you're implementing it for the cryptographic challenge of it, I think it still makes a lot of sense to try the ZKP and try to verify every move after every move. There's definitely some value to that. And what I was saying was the point that the main big picture that the conclusion that we need to make from this ZK fellowship stuff is that ZKPs were enough for this game because essentially the private states are not really interacting. You have your private ship configuration to yourself, they have their private configuration to themselves, and you're just attacking them publicly. They are attacking you publicly, but your private game states are not interacting. Then you can even split the game into two completely separate games where only you're attacking or only they're attacking. So you can think of it as sort of like a merging of two games where you play one by one. So that was my conclusion about why using only ZKPs was enough. Like if the ships were attacking each other and you were just on the same, let's say for example, there's an option to move your ship and you were on the same sea, then obviously you would have to know about the other person's ships to see if you can actually move or not. But you don't really have that. You don't really interact. So that was like my main conclusion. And then I was aware of the StarChess game, and then I thought, can we break some bolts and can we actually make something work to use that? And so that's how I came up with the idea.
Cool.
That was like the background.
So from my understanding, the two pieces are you're using ZK to prove that your piece is moving within the rules, and then you're using MPC to calculate if if either king can see each other, or I guess if both kings can see each other, right? Is that correct?
Yes, in like the general idea, yes. It's like a collaboration. You need ZKPs to make sure that people are actually inputting the right things to MPC, and then MPC takes care of the rest.
Okay.
Yeah. Now I'm doing the implementation. Actually, you realize that there are many things that you need to consider, and many
It's on the detail.
you will do the MPC, but you also need to prove that you're exponentiating every element in the set with the right exponent. So you need ZKPs for that. It's like an entanglement of ZKPs, and it just gets mixed up.
Yeah.
But in a general idea, the move step, at least I personally, in my implementation, I separated the move operation from the PSI, the MPC operation. So first, you make a move, and then you prove to the other person that it was valid, and then there's this MPC process that happens to update your board, and then there's an identical and symmetric process that happens to update the opponent's board.
Without revealing anything.
Without revealing anything. Yeah.
So you have been mentioning a couple of times already the word MPC. What does it stand for, and why is it actually solving the problem that ZKPs are not able to?
Yeah, so MPC stands for multi-party computation. I guess in my version we can say it's two-party computation, but it's the same umbrella. And the definition of MPC, I guess, is it's just the family of protocols that allow parties to do some computations over their private data. Let's say one example that you can find online is, let's say there are a group of factories in the economy and they produce the same thing, let's say teddy bears, and there's some common good in all of them, calculating the total output of the economy, the total teddy bear output of the economy. Let's say, I don't know, for policy reasons or stuff like that, But they obviously don't want to reveal their individual output levels, output numbers. And so if we abstract this problem, what we see is, let's say there are 5 factories. We have 5 numbers, each belongs to one person on the table, and we want to calculate the sum of these numbers without revealing any one of them. And so in that case, MPC can help you because it helps you keep the numbers private while calculating the sum, basically.
So if I were to summarize it, you would say like CKPs are good to prove something about a secret that is individual, and MPC is to calculate or collaborate with secrets that each person has without revealing them. Or how would
I
you?
guess,
Mhm.
I guess yes. I'm not really an expert. I don't want to say yes or no.
Yeah.
Because I'm also getting told that zero knowledge proofs are just a certain subset of MPC protocols.
Interesting.
Because we have ZK snarks, but
Yeah, we got interactive.
initially
proofs as
those
well.
zero knowledge proofs are interactive.
Yeah.
Right? Then you can also say, oh yeah, that person has a state, private state. If we come to this graph coloring problem,
Yeah.
right? The quintessential example, you can say they just have a private state, and they want to prove something public or run a function,
Yeah.
or just private data without revealing. So I think to define connections that they're all on the same thing, whatever. But I'm not I'm not really an expert, so I'm not really sure.
Yeah, makes sense.
One thing that I wonder now is, in this case, we just have 2 different parties, right? But to make the analogy in chess, we have also 4-player chess, right? Where like you are basically competing against 3 other people in a kind of table which has like the shape of an X, to put it in some sense, or a plus sign. So if we kind of abstract it on this way, it seems that we could have 4 parties, or we could have at the end n parties, right, that are doing this kind of computation. What I wonder is, they need to talk to each other, right? Or at least they need to find some abstraction that mimics the communication that they would have. Can you speak a little bit about that? Why do they need to communicate? How do we prevent communication overhead? Which is the state of the art in that sort of topic?
This is a difficult time. I'm just trying not to sound like an expert. I don't know. Because I'm not an expert.
Everyone here says they're not an expert, but these are some of the experts. Like,
Okay, one thing I can say is, I guess, as a general pattern, the way you prevent these messages from revealing information is by using some cryptographic assumptions, like the discrete log problem, right? The discrete log assumption, or the prime number assumption. I don't know the official name. So you just send a message that, let's say, okay, we can give a more concrete example. Let's say you have a generator of a group, and then you exponentiate it, and then send the exponentiated version to the other side. And because we have this discrete log assumption, they can't get your secret, which is your exponent from that, but they can still make some calculations on this data. Let's say something like exponentiating their own stuff and then multiplying with what they got from you, and then due to some mathematical properties, let's say the output of that does not reveal neither mine nor their exponents, so secret, but we get something meaningful from that. So that's, I think, in general, how these things work. These messages should not reveal something, and they always refer to some assumption at some point on the chain, this reference chain. It boils down to an assumption that we assume is true, basically.
That's nice. So, zooming out a little bit and going to your experience again with this project, you basically saw these focus watches and you decided, let's give it a try. So how do you start? Is there some tooling that it's like the de facto way of approaching those things? Did you need to make your own tooling? Which are the protocols that you started to check first and that you maybe discarded? Like, what's the history of all of this starting path?
That's a good question. How to start? I know in August 2022, I made a bunch of forum posts. Like Zero Knowledge FM, a few others, like 3 or 4 forum posts. And actually, after writing it first, I realized, wait, I can just copy paste. I'm not sure if this is good forum etiquette, but I decided, these forums are not that popular. They can just benefit from having the same question, having some posts. So I wrote the first one, posted that, and then copied from the first thing, and they were all using the same software. I don't remember the name. But then I copied and pasted to the other forum, and I pressed send, and then a minute later I received a notification saying my account is blocked.
Oh wow.
I think that was because they have like some sort of an automatic check.
Yeah, spam.
Like the spam filters. But yeah, I think that was the beginning. I just made a few posts, and then I had to contact the admins to unblock me. And then I received a few pointers. I received one link to Zama, for example, Zama.ai. I think they're working on some sort of homomorphic encryption library, right? And I think then I started learning about homomorphic encryption. And I guess that's also when I decided to name the game. The name of the game currently, and as I always say, I need to change the name. It's Zero Tag, so ZHERO, capital TAG. And the meaning is like zero knowledge, zero, the number. And then, like I was saying, I was thinking of homomorphic encryption. Maybe I should use homomorphic encryption. So I said, let's have 0, but homomorphic encryption is HE, right? So I said, let's call it 0, ZHERO. And then tag is like this game that people play. I still don't know what exactly it is, but I just know what kind of a game it is. So I called it Zero Tag, mainly because I thought it was like a homomorphic encryption game. And then I started learning about MPC, because HE and MPC, I guess, go hand in hand. And then I joined a few Discord servers. One of them, it turns out, was a Halo 2 server. I still don't know what the connection between that server and you is, if like the Halo 2 team here, I just don't know. But there's
I think we use it a lot.
We can explain.
Is this are we allowed to use our computers?
Yeah.
What's the...
So, Halo 2 is made by some people at the Zcash team, right? It's like one of the lead developers is Ying Tong, who's here. So she's like loosely affiliated with both PSE and OX Park. Like we're all, I guess, kind of friends. I don't know. Like there's so much like intermixing.
We collaborate a lot together.
Yeah.
Okay.
That might give a little bit of context.
Yeah, it's a small community still.
So I did find the server. It says Halo 2 ecosystem, and the symbol is H2E. So basically, I made a post. I sent a message here, and they invited me to their weekly chats or something over Discord. And I had a friend who was helping with this, and we joined together. And then I, roughly explained like what we're trying to do. And they said, yeah, that's very nice. Check out these links. And they sent me, which I can see here, a link to like an academic presentation that goes through some PSI protocols, which is like an MPC subset, which I should explain. And then, you know, I looked around and then I found I realized that one of the PSI protocols was actually useful. And then, you know, I wrote the algorithm and stuff like that. But coming to PSI, I think that would be, you know, worthwhile. PSI stands for private set intersection. And it's a protocol family that is a member of the MPC family. And the goal is so let's say you have two parties. Party 1 has a certain set, party 2 has a certain set, and let's assume the sets have the same types, let's say just numbers, just integers. And they're trying to calculate if there's an intersection, if they have a common number. And so PSI can help with that by, PSI basically does, what PSI does is it gives you a protocol such algorithm that helps these two parties calculate the intersection without revealing anything else. If there's an intersection, you see the intersection and nothing else. If there's no intersection, then you just don't find anything else. And the PSI that I'm using specifically uses the Diffie-Hellman stuff that I was just mentioning, like having a generator and then exponentiating and stuff like that. And I just explained it shouldn't be that complicated. But when you make a move, you first prove that it was a valid move.
Yep.
Like, that was the first thing. And then, like I said, you need to update both cores. What I realized was it's essentially you can abstract this problem to saying, is set number 1, which is the squares that the white king can see, intersecting with set number 2, which is the position of the black king. Yeah, that's like an abstraction. And then I said, okay, if we can convert these coordinates, the xy coordinates, into a certain form that we can input to this algorithm, this PSI algorithm, then we can essentially calculate if, for the first PSI at least, if the white king can see the black king. Right? That's essentially the idea. So set number 1, because it's a king, it's only the neighbors around the king. There are only 8 squares, so 8 values in the first set, and then only 1 value in the second set, which is just the position of the black king. And then you run this PSI. You first exponentiate all the. So let's say white moves, right? And then white first calculates the coordinates of the squares around itself, and then pick some random number, which is their secret for PSI. They exponentiate all these values with alpha, and then it sends it to the other side, sends to black. And because of this Diffie-Hellman, this discrete log assumption, again, when the black king receives those 8 values, it cannot calculate the coordinates. And so what the black king does is it picks its own randomness, which is beta, let's say, and then exponentiates these values again. So at this point we have these 8 values exponentiated with alpha and then beta, 8 of them, and the black king sends it back. And at the same time, while sending it back, it sends something else, which is its current position, exponentiated to beta, right? So received 8 alpha exponentiated values, exponentiate them with beta, send it back, and with it, exponentiate its current position, and send that back. So the white king now receives these 8 values, alpha, beta, and then the single thing, beta, right? And again, because of the discrete logic assumption, it cannot deduce anything about the position of the black king. So it receives these, and then exponentiates the single set with alpha. And now what the white king has is 8 values exponentiated first with alpha, and then with beta, and then a single value that was first exponentiated with beta, and then alpha. And because this exponentiation is commutative, so because of the property of modular exponentiation, and fields exponentiation, whatever, if you exponentiate with alpha and then beta, the output is equivalent to exponentiating first with beta and then alpha. And for those who are not familiar with these concepts, it's essentially like how 5 times 3 is equal to 3 times 5. Right? So it has these 2 sets, doubly exponentiated, and if one of these values, if the value in the single set, the set with the single value, is equal to one of these 8, then it says, oh wait, we must have started with the same coordinates if we reach the same value. That's also one of a property of the math that we're using. Yeah, that's basically the idea. And so at this point, it's only the white king, right? The black king just followed the protocol, just did whatever it was supposed to do, and doesn't learn anything. So it's only the white king that has this information, that can update their own board. So we now do the symmetric thing with the black king. They calculate their 8 squares, send it. They have now their own alpha, and then we'll have alpha prime, beta prime. It's essentially the same idea. So the first PSI updates the white king's view board. The second one updates the black king's board. And you might ask, what's the point in doing this 2 times all the time if when the game finishes you can actually see the other side, right? If white king is seeing the black king, at least in this version of the game, then it's necessarily the case that the black king is also seeing the white king. And I guess we could just make it much simpler by, I don't know, maybe canceling some, combining some sets and stuff like that. I didn't really pay that much attention to that because I thought, we're working on a simple game, but the goal was always to make it a bit more complicated, find a general solution for a more complicated game. And if you are, let's say, implementing this for the case where you have communication, vision cones, then the white king can maybe see the black king, but the black king might not be really seeing the white king. And so in that case, you probably can't really do those small tricks that you can do in my game because they can see each other at the same time. So I decided to intentionally keep the PSI protocol general, so that it can be generalized later. And one implementation detail that I realized is, it's nice. Obviously, you can see if the game has finished or not, but it would also be visually nice if you can actually see at which position they were in, instead of just saying, okay, I'm supposed to see that person. And the way you do it, at least the way I did it, was you have a certain logic in the zero knowledge proof, right? It's at least in my version, it's the zero knowledge proof circuit that calculates the 8 values around your current position. And what the first element of this 8 element list is, because it's the circum circuit that's constructing it. It first adds, let's say, the top left corner and then the mid top whatever corner, top right corner. So you just keep track of that, and then depending on which element of the list is the same, you can deduce, oh wait, then it must have been the top left corner that the opponent is. And yeah, at this point I should also mention, because I mentioned zero knowledge proofs, but where did they come in? In the MPC that I mentioned, we just assumed that everyone's just following the protocol. Everyone is exponentiating at the same values. They're sending the right values back and stuff like that. I think my PSI, the PSI that I'm using, is a semi-honest PSI, which means that if the parties are if the parties are following the protocol, they can't learn anything if they're following the protocol. And so this is called the semi-honest model of these things. And it's not just for MPC, but for some other stuff too. And there's the malicious version. There are these malicious protocols that prevent people from learning anything, even if they're intentionally misbehaving. Whereas the semi-honest one, we expect that they will follow the protocol, and we expect that with the things that they receive from the protocol, they can't calculate.
Yeah.
And so I learned that it's a general pattern to start with the semi-honest protocol, and then use zero knowledge proofs to sort of turn it into a malicious protocol by sort of this is like a small hack basically.
Yeah. To constrain it more, to prove more.
Yeah. Instead of making a much more complicated protocol with maybe more overhead or more messages, or just more complexity, you start with the semi-honest protocol and then attach zero knowledge proofs to these messages. And that turns it into a malicious protocol. Right? So that's why I need ZKPs, and that's why MPC is not enough. And just to reiterate, if you don't use ZKPs, there's no guarantee that the two parties are actually inputting the elements that they're supposed to input.
Right. They could cheat. They could
Yeah,
teleport
exactly.
across the board.
Yes. Yeah.
Yeah.
And this comes back to the idea of we can't calculate the secret from the message, right? And that is the same reason why we can't see if they're cheating.
Yeah.
Because if we could see that they were cheating, then that implies that we could calculate their inputs in the first place, which just contradicts with it being actually secret. So there's this tricky situation where you want both sides. But yeah, so that's why we need ZKPs. And to dive a bit more into the implementation, just more specifics. We first proved that the move is valid, right? That was separate from the PSI, MPC, and then you prove that the elements that you input to the set are actually around the square where you're at. And again, this is ensured by calculating the hashes all the time. You have a position commitment, a hash commitment to your current position, and so this cert calculates and then proves that it's the same hash, stuff like that. And then you also need to prove that you exponentiated every value using the same alpha. You send that to the other person, and they need to verify that you did all those, and then they get the public signal, and then they need to prove to you that they use the same beta for everything, and then they, like you did, need to prove that they're using their own position with the hash. It's very tedious. And they send that back to you, and then you verify, and all that.
Yeah.
So MPC covered with zero knowledge proofs, basically.
So right now, for each movement of the piece, how many, let's say, back and forths interactions happen between these two parties? And do you see any opportunity kind of like to reduce that? Or, yeah.
Yes, that's actually the next step in the journey.
Nice.
But yeah, that's a very good point. currently, at least currently, meaning about what we have talked so far, we have, I guess you can say maybe 5 steps after every move, and we will be cutting this down. But let's start at 5. And it was, you make a move, you make a proof that it's valid, then send it to the other side, and then don't wait for any replies. You just start the PSI for yourself, send that, and then receive something back. So that makes it 1, 2, 3, and then they start their own PSI. That makes it 3 and 4, 4 and 5. Right, so 5 messages. And the first realization we have is we can just combine the first move proof with the first step of the PSI.
Yeah.
Right? So there's no point in just saying them separately. So now from 5 we have 4.
Yep.
It's like the prime gap thing, just bring it down. Now we have 4. And then, so you have 1, 2, and then 3, 4, right? Paired together. The second realization is when your opponent replies to you with your first PSI, they can also just simultaneously start
Their first.
Exactly.
Yeah.
Exactly. So it becomes like a Z shape, right? Basically, instead of having like I don't know what brackets, angle brackets.
Yeah.
You get a Z shape of communication.
Yeah.
So that brings from 4 to 3. And our current thought is that if you use MPC, you can't have fewer messages than 3. I put some serious thought in this. Because I was just not satisfied with 3 messages. It was also very tedious. You don't want to implement all those steps. There was also some practical implications of having 3 messages. And I came up with an argument as to why you can't have less than 3. And I guess, how can I say this? Okay, so these 3 messages were to update 2 boards, right?
Yeah.
The thing that I realized was that to update 1 board, you need at least 2 messages. So that implied that you can something like that. And the argument is, if you make a move, just to see the problem description, we're checking if the following thing exists. If you can do the following thing, you make a move, you send something to the other side, and that is enough information for them to update their view. That's what we're checking. Is that possible with MPC or homomorphic encryption? Again, there's this divine connection between homomorphic encryption and MPC that I'm not really sure. So I'm just saying MPC/homomorphic encryption just in case. So yeah, we were just checking if such a protocol can be made with MPC and HE. So the thought I had was, if you can send a single message that contains every information that the other person needs about your position to update their board, then there's not much that prevents the other side, your opponent, from running this whatever using not only their position, but on also any other position on the board. Like this is a bit. This is not like a formal proof or anything, but it's just an observation. Yeah, they just receive something that contains some information, some private information, mixed information about your position, and that's sort of enough for them to calculate their own board. And so we expect this process to happen like they receive this, they input some private data about their current position, because they're honest players, and then they reach something. And well, you can say, honest players, it's fixed, right? No worries. But if they're malicious, well, we can just expect them to send the proof back, saying, I actually ran whatever you sent me, ran this algorithm with the position that I have right now, or something like that. You can make a ZKP. And so the game can move on, and maybe we can reduce it to only one message or something like that per board update. But then the problem with that is, okay, they can send you zero knowledge proof for that, but zero knowledge proof only proves that they ran this algorithm at least once with their current position. It doesn't show them anything about. It doesn't show you anything about what they did locally. You don't know what they're not sharing with you. So this is a bit again. It's a bit informal. It's not that formal.
Right. You need to have some negotiation back and forth, or someone may be able to infer information out of it.
Yeah, something like that.
Yeah.
So ZKP does not really protect you. That's the point I was trying to make.
Mhm.
They can run the same thing using some random position on the board. See locally. Oh wait, they're not here. Let me try over here. Oh wait, they're here. So let me just not.
Right.
Maybe.
There's nothing stopping them from just running it on every spot on the
Exactly.
board. Yeah.
Exactly. But to make them feel like they're secure, let me just run the zero knowledge proof with my current position and send that back.
Right.
But they can still calculate all that. So that was the observation that I made, basically. And again, it could be wrong. It could be wrong. But that's what I'm trusting currently. So just to recap, the conclusion I had from that is to update a single board using MPC and HE, you need at least 2 messages. One message is not enough. And so if you just multiply it with 2, you get something like 4, right? At least 4, but then you can do this, again, this angle bracket and Z trick.
Overlap,
Reduce to 3. And so, long story short, MPC plus HD, you need at least 3 messages. That's currently what I'm thinking is happening.
Yep.
For 2 boards.
For 2 boards.
Yes.
Yeah. That's a good point. If you want to update
Both sides.
boards
Right.
after every move.
Yeah.
You just can't get everything. Basically, that's the conclusion.
That makes sense. So I'm looking at your circuit. So you have the move circuit. So there's really 4 primary circuits. It's the proving you moved correctly, and then the 3 PSI steps, right?
Yes.
It's you sending a message, them sending it back, and then you putting it together and verifying that there's no intersection.
Yeah.
Okay. Cool.
Yeah. There's some. For example, the PSI 3, last one. You can argue that you don't need to really verify that third step when the mover receives it from the other person back. They can just calculate and update their boards, but they don't maybe necessarily need to send something back to prove that, because the other person will also do the same thing.
Right.
They also realize, and again, this comes back to the idea of, in my game, they can see each other at the same time. But I decided to keep it general. And, I still do the verification of the third PSI no matter what. And it turns out actually it takes around 10 seconds to update a single board. So 20 seconds in total.
Nice.
If you add the move ZKP, maybe you could say maybe 8 or 9 seconds per board. And it's a long time. Making a move and waiting for 20 seconds. But on the other side, how many ZKPs are we preparing and then verifying? Maybe it's just, that's maybe what we can get with the current ZKP infrastructure we have. Maybe it's more of a Halo 2 problem or a Circon problem at this point.
And I think it's worth mentioning that that's the state of the art now, without many crazy implementations that maybe we can look at per game, but that this is still a very good mental model primitive example that then many other game developers could see this mechanics and start thinking, okay, how can I optimize this to be microseconds or something?
Yeah, and here's the interesting part. The catch with what I was saying about the three messages was that it was if we are using MPC and HE, there's a catch.
Mm-hmm.
But it turns out there are other stuff that we can use, maybe witness encryption. And if my understanding is correct, we can use a single message after every move to update everything, to make sure that everything is okay. Witness encryption. I was talking with Sora, and I used to, and yeah, that's currently the consensus. I feel like we can actually reduce it to one message, or again, maybe two messages if you do the Z and bracket trick, but less than three.
Would that still require you to use CKPs? Because that witness encryption thing sounds like you might have the chance to press sin of the CKP depending if it's about leaking data. Maybe you still need to prove the correct position and hence you cannot prevent the usage of the CKP anyways.
I'm not sure, but my intuition tells me that some sort of ZKP will still be necessary.
So
if I have to bet, I would probably say. Yeah.
So in that track, and from the perspective of an engineer that likes to over-optimize things, you said that there's a lot of proving steps, right? And you do many rounds because until one king doesn't find the other and it kind of eats him, to put it on some sense, you still need to prove at every single step or at every single move that you did things correctly with a CKP. So do you foresee any kind of improvements if we try to apply proof aggregation into all of that, so that you don't need to verify stuff at every single move? I just prove you that I accumulated correctly all of the proofs that I should have sent you, and at the end you simply verify the entire thing.
If I have to bet, I would say you probably can't optimize. That's because it's just built into the game, and that's just how the game works. We can connect this to the Battleship idea, like how I was saying in Battleship, you can just play the game until the end. No one can send any ZK proofs, but at the end you can just show that you're all behaving right. But in this game, to be able to play the game, you need to send those messages. So, my first thought is that's probably not possible just because of construction.
That makes sense. Also, you have talked a lot about HE, which I guess stands for homomorphic encryption.
Yes.
What is it? What kind of properties are we looking for that? Like, what does it enable us to do? Sort of, could you give us like a really outer overview of the topic and why do we need that and why we are talking about that? And does it have to do with this kind of exponentiation technique? What is it about?
I know less about HE than I know about MPC and ZKP. I can't give examples of actual concrete examples.
Maybe just an intuition over the idea would definitely work.
You can say doing computations on encrypted data and the computations on the encrypted data having the same outcome as the computation on the plaintext data. So that's like the essence of homomorphic encryption. One example that's given is, let's say this arrow represents the computation, and so this is like the plaintext world, let's say. So when you make the calculation, it brings you from here to here, right? Make the computation to the result. So what homomorphic encryption does is you have an encrypted data, the same data, encrypted version.
Mm-hmm.
And so homomorphic encryption is the arrow that brings this to this.
So we could see it on the way you are framing it looks like if you have a vector on a plane and you escalate this vector and you get a linear combination of it. But with your example, it looks like you are keeping the relation and you know that the relation holds. What you are not keeping is any way to like undo the linear combination to get to the primal vector that you define.
Yes, so so in no place in this computation, this homomorphic computation, this arrow, you can take this and bring it to the plain text format.
Mm-hmm.
So it's sort of, there's this clear separation between who can encrypt, and who's encrypted and who's encrypting and who's computing, making this computation.
Mm-hmm.
Just like a square, basically.
Yeah.
Instead of doing this, you just go up first, encrypt, and then do the computation.
Mm-hmm.
And when you decrypt, it brings you to the same place. Do you know the bear question? Wait, this actually.
Which one?
Yes. So the question is, you have a bear, you go 15 kilometers to the south, you go 15 kilometers north, and then you go 15 kilometers east, and then you go 15 kilometers to the south. What color is the bear?
You can tell differently, right? I mean,
Wait, sorry. Did I tell you that once you go 15, when you go down 15 kilometers south, you reach where you started. The place you started.
I see the question.
Wait, that was the whole point. Why did I not say that? Yeah.
I've heard it. Now I remember.
Yeah. So what's the color of the bear?
It's white.
It's white, exactly. Because it must be a polar bear. Because if you go north 15 kilometers, that's
Okay. Okay.
So
now I see. Okay.
So connecting the polar bear to the homomorphic encryption.
Yeah.
So it's like, you start over here. One person just does the computation. The other person first encrypts, does the computation, decrypts, reaches the same place.
Okay.
That's basically the essence.
Yeah.
Cool.
But yeah, so a more concrete example is you encrypt your data, send it to the server or someone, and then they make a computation on this encrypted data. And let's say you pay for the service, and you get the result back, and you decrypt, and it's actually the computation that you want. Whereas, I think it's also useful to say why it's different than what we have right now. When you encrypt something now, it's not now, but it's non-homomorphically, then it's like mixing it up and no one knowing what it is. Except if you have secret key, private key, only you can decrypt. But if it's encrypted, it's just mixed up. Whereas in homomorphic encryption, you have this mixed up thing, but at the same time, some properties are preserved so that when you do the computation, the mixed side can still hide what's happening, but you get the computation. You get the necessary properties still there. Yeah,
That makes sense.
Yeah, I also heard full homomorphic encryption,
Yes.
and I wonder if there's a difference. It's a topic for that.
I actually don't know what separates fully homomorphic encryption from homomorphic encryption.
Neither.
But yeah, so witness encryption, is it related to homomorphic encryption? Yeah, again, there's this whole umbrella, this whole family. I guess in the end, we're all going to die, and everything's related to.
Everything is MPC.
Yeah, everything. Yeah, I think in the end, everything is indistinguishable. Wait, what is this? distinguishability, obfuscation, or something.
Yeah. These are just tools we use to solve our problems.
So I saw you're using a 6x6 board, right? So that's like basically like the simplest board you can make and still have some fun,
Yes.
right? Like, so if and when you expand this to a normal size chessboard, how much more difficult is that going to be? Is that just going to increase the proving times, or is is that much of a factor at all? Or are you just picking 6x6 now just because it's easy?
Maybe the direct answer I can give you is I thought let's not make things more complicated. It will probably take more time and stuff like that. But to be honest, I actually never put very serious thought into how much am I using this 6x6, like the 6 side. Actually, it might not take longer if I do 8x8.
Right.
Which is a bit embarrassing, because I just input the boundary value. I don't create a 6x6 array.
Right.
And that would,
Because you're only really figuring out what's around the king.
Yes,
That's all you
exactly.
care about.
Yeah, exactly.
So that's what I was thinking. It's like an 8x8 board is like, I don't think it's going to be that. My intuition tells me it's not going to be that much more complex, right? Or add much proving time. Really, if you go to a different type of chess piece, that's when it's probably going to skyrocket, right? Like you move to a queen, and it's like, well, fuck. All right, now it's now it's way more complicated.
Yeah, that's a good point. To be honest, I didn't really pay that much attention. I was just thinking, for them to come together and actually see each other, how many steps do we need?
Right.
8x8, 6x6. I said, let's just go with 6x6.
Yeah. So 6x6, like that's that's just going to be a shorter game, right? 8x8, if you have some clever people, like it might take a little while, right? One other thing that I thought about the other day that I think would make this interesting, if you kept the 6x6 board but made the board modulo, so you can loop over to the other side, so you basically just have like an infinite canvas. I think
Like
that'd
you
be a
go
lot of
through
fun.
one side and appear on the other.
Yeah.
Okay.
But you're still only limited to 6x6.
Yeah.
So you're still always going to be close to the other king, but you're not going to get cornered, right?
That's interesting.
That's interesting. That's also similar to them sort of moving around the sphere.
Right.
Yeah.
Right.
Yeah.
Maybe it's not directly so. I need to check the boundaries conditions, but I think it's like a similar idea. Right?
Yeah.
That was fun.
I think that'd be fun.
I think there are many variants, like the fog of war or the pieces.
Yeah.
I did have a question about future improvements and even like future applications. Like I'm thinking, like if I'm listening to this and I have an idea of a game, which would be like good games that I could try, or which characteristics should I take into account for trying MPC and CK?
Can you say that again?
Yeah, sorry, it was a long question. So what are some possible ideas of games that you can make with MPC and CK? If you have the idea, perfect, and just the name of the game, or which characteristics would they need to have?
I currently think that there should be a way to pretty much play every game using MPC. That's what I'm sort of thinking. Because I think this is a similar moment as once you prove that you can do this Halo 2 with addition and multiplication, it just shows you can do every computation sort of thing. I feel like if you can make this game, you can probably make every game using, honestly, probably more complicated things. But I think it's sort of like an existence proof in a sense that you can do. But yeah, I mean, probably you can do pretty much every game. But coming back to witness encryption, something that witness encryption can add while MPC cannot, is maybe this can be an argument for why MPC cannot actually do every game. Because the MPC requires them to be synchronous, right? You actually need to have the other person to reply to you so that you can learn. But some games, I know the gamer, I don't know many games, but there you go. Maybe one of these, say, city building games where you fight against someone else. You go to sleep. You don't wait for the other person to finish their stuff. You don't sleep at the same time. So you need some sort of asynchrony for these games. I think MPC will probably not be good for that, and witness encryption is actually very good for that. Because the whole idea is, you make a single move, right, and then you submit to the other side, and that's enough for them to play their own game, sort of. So, yeah, that's one realization we had recently. And it's not just about bringing number 3 to 2 or 1. It's also about switching from synchrony to asynchrony, possibly. Yeah.
So, to follow up on Andy's, if you could, basically ask for a wish or a couple of wishes in regards the actual tooling, the state of the art, and how would you like to see it evolve, so that your game was maybe easier to develop, maybe much faster, maybe, I don't know, whatever kind of improvement that you have told us that could be feasible, which is that thing or that things that you would like to see happening so that they could make the game completely playable with a full chess board without long waiting times, all of this kind of stuff?
I think some tooling for MPC stuff is probably not a very creative answer, but I think that's, I think some more tooling for MPC. In general, about games, I think having some sort of a game engine would be more useful. Because you sort of have a basic level for every game, a basic infrastructure for every game, and networking layer, or ideas like position, location. So I think you need more of these infrastructure into stuff. I know there's mod, right? Mod is working on this. I think that's very useful, I would say. Yeah, I think those are the main things. Yeah, and maybe more research about witness encryption, so that we can switch to the asynchronous version. And something else, I'm realizing that there are many researchers working under the same umbrella, but there's just a bit of a confusion about the terminologies, not on the side of the researchers, I'm sure, but from the side of non-researchers, non-academicians. I'm still struggling with the differences between, again, I was mentioning this all the time, MPC, how is it related to HE, are they cousins or brothers, or father, son, it would be nice to see how actually they're related. I can count to names like homomorphic encryption, fully homomorphic encryption, multi-party computation, secure multi-party computation, non-interactive multi-party computation, witness encryption. I'm sure if I go down and check all these papers, I will actually see, but having them together and having this conversation with terminology that is not supposed to be useful. Because now I'm claiming, yes, we will use witness encryption, it will be very nice, but on the backside, I'm still not sure. Am I looking for non-interactive MPC? Am I looking for MPC in the head? Am I looking for witness encryption? or can I even do witness encryption? Is this what I'm looking for? Stuff like that. I think just more clarity.
Yeah. Who do you think we should bug about that?
Like who should?
Yeah, like is there anyone
Bother-
here
bother.
that could answer those questions?
Probably Sora, Ayush. Those are the ones who I will not name who of the two it was, but there's a 50% chance that you can guess. But one of them claims that both of them have them combined. He claimed that both of them combined have access to all of its description papers and they all know what's going on. So probably I can ask them. Yeah. And also sorry, Ying Tong was mentioning MPC in the head. To be honest, I couldn't really get it. I need to sit down and actually read myself.
Do you think that the ecosystem and in general the rhythm at which papers and new techniques and maybe implementations are coming out is similar to the CKP world? Do you think that maybe getting up to speed and getting up the level of production ready things that we're getting nowadays in regards of zero knowledge protocols, all of the implementation and open source libraries that you have access to, all of the documentation that you can find online by lots of various people. Do you think that getting these sorts of things into the MPC world first is feasible and second is actually something that could help?
I think it will definitely help. So you're wondering about the progression of technology and if it can have a trajectory like ZKPs?
Yeah, exactly. Because at the beginning in ZKPs we were kind of like in the same place. There were those gods that understood how everything worked, right? And there were some libraries that were like tedious to understand and tedious to use for the end user at the beginning, so that you really needed to understand what was going on in order to use them, right? And nowadays we have Circon, we have plenty of libraries and implementations, lots of documentation everywhere. We have podcasts, we have talks, we have events. So there's like a lot of places where you can now gather information and all this kind of stuff. Do you think that MPC could kind of take a similar path and like follow the steps that the ZKP ecosystem took?
I think it's bound to go to that direction. I think that's destiny. That's what. Gross 16 is 2016. Oh wait, that's why. Okay. That makes sense actually.
And Planck was 2019. Is that right?
I think so. Yeah. In September, I think it was, right? When everything came out at the same time.
The same month, right?
Yeah.
What is snark number?
So basically, there were like a cascade of papers in relation to zero knowledge proving techniques, and all of those papers came out in September the same year, with like very few days of difference. So that's why the fact that this happens basically is why I basically ask you if you. I don't expect now that we have like contributions to the MPC field like every day or every week or stuff like that. But this is what is actually happening in the ZKP world, right? Like every week, every 3 days, you have a new paper that does something, changes something, figures out new ways to go, whatever. And for what you told us, basically, it looks like this is kind of the needed direction in MPC, so that lots of problems can be solved, and it's easier for people to get into the field, right?
Yeah, I feel like, and was told by some people, that we're sort of in the 2012, 2013 times for MPC.
Mm-hmm.
If we check the ZKP timeline, that's nice.
Still a lot to grow.
That's nice.
Yeah.
That's good. Still early.
I guess I will make my last question probably, and is we have seen that we can actually do a game where we can play chess in the fog of war without trusting on anyone, and that's completely fixable, right? We know how to do it. You basically went through all of it, and I think it's clear for us which is the general idea and which techniques are you using. My question is now, okay, we can do games. Which are the examples for like the real world applications that we use day to day that you think MPC could trigger and could try to solve in the near and in the long away further future?
It's a bit hard. I can think of some general areas. Just like how in the 70s and 60s, people are asking, we can already do this on paper. Like, why do we need computers? And I'm sure, those people had some ideas about how they could be used. Yeah, I know. Maybe it could be a bit faster to make the addition. Maybe I can send a bit more data abroad a bit faster. But they probably weren't really imagining what we have right now. And I feel like, when I talk to people, that's usually the answer that I get. You can see, okay, having private data and making public computations, I can see why it could be helpful. Maybe some financial applications, privacy stuff, and scaling stuff. But it's a bit challenging to say, here's an example. You can call this protocol like this, and there's just stupid company name that can do that. It's a bit hard to point them down.
Yeah.
If that makes sense. But I can definitely see a lot of things. Another way to say is, I will not be surprised if everyone uses MPC every day in 15 years maybe.
That's a nice way to put it.
Yeah.
It's really hard to see how exactly they will be used, I would say.
That's fair. There's a lot of obvious things immediately, but yeah, everything that can be built on top of it's really hard to predict. Yeah.
I feel the same way also with quantum computer stuff. This is a bit far-fetched, but you can actually simulate human brains if you have quantum computers. I know it's not my thought. I'm just reflecting some people's thoughts that I read.
I like the example that was shared last week, which was how do you have certain in a negotiation in peace talks in a war, like how you as a country make a list of demands and offers that you're willing to do, and the other country does the same, and then you find an intersection. So that could be an amazing tool for diplomacy, right? And try to help humanity to have more coordination. How can we use this principle that you did with MPC in this little game for amazing and huge stuff?
Yeah. The salary negotiations that were brought up last week, that's
awesome.
Business deals, all of that's pretty interesting use cases for MPC.
Yeah.
Honestly, I would really like. I don't know if this would fall more into. It would probably fall more into ZK, but stopping cheaters on online games. There's a big problem with people cheating in games, but you add in provable computation or multi-party computation, then we can solve a lot of that. We just need a hell of a lot of power.
Yeah, something that I was thinking of, and I don't have a very precise way as to how MPC can solve this. Front running stuff, financial applications. I feel like it can really fix that.
Yeah.
I know there's some ZKP solutions to that as well. I just don't know the details, but I think MPC can actually solve it, I guess. But ZKPs are MPC anyways.
Yeah.
So maybe I didn't add any information.
Cool. Well, I appreciate your time. Definitely.
Yeah.
This is interesting.
Yeah.
So you leave this week. when can I play your game?
So I can tell you what's happening right now. So I'm someone who really likes designing algorithms and protocols, but I just don't like front ends.
Okay.
And then I realized. So I was not really planning to make a front end for the game, and then I realized if I don't have a front end, then it's not a big game. It's just a few test cases, and then some functions. So I started with some React front ends. I was starting with React, learning React, and then things just didn't work. And then I decided I should probably not spend that much time on React, and also some implementation detail. It's 6x6, right? First, I was thinking, I want to have a front end, but I don't want to work on it. So I was looking for some chessboard implementations. But everything's 8x8, not 6x6. And obviously, maybe I can change, right? Playing with some numbers, but I just couldn't find anything that allowed me to have a few fixes. But I was just too impatient to actually understand all the React stuff and going on and just fix everything. So currently what I have is I'll be working on a command line interface that explains everything, prints two boards, says, we're doing PSI right now, PSI 1, these are the coordinates, whatever stuff like that. I think that's the middle ground.
That's reasonable.
Okay, now that I said this during the recording, I think I actually should need to.
If you make a command line,
I was working on it. It's not like I made the progress here, but now I need to actually finish that.
If you get it to the point of having a command line version working, then I'm sure we can find someone to throw together a front end for it. You've done all the hard work, so cool. Well, definitely appreciate it. Do you have any questions for us at all?
Not right now, no, thanks.
Okay. Cool. All right. Yeah. Thanks.
Thank you for being here.
Yeah.
We appreciate it a lot.